So yeah, today I was just going to try and give you a bit of an overview of what's going on in the world of marine propulsion, marine engine emissions, and how we're controlling those emissions. So firstly, probably to give you a good solid background in what do we actually mean when we talk about emissions. And then we will just look a little bit, and I don't want to get too bogged down in the regulations, but just look a little bit into what are the current and future marine emissions, what are some of the trends, and then really start talking about alternative fuels, which is how we're looking to deal with a lot of these issues, and particularly also power-to-X, which is around synthetic fuels, and essentially sequestering carbon into a synthetic fuel synthesis process. It'll become a little bit clearer what that actually means for shipping when we get to that area of the presentation. So firstly, what do we mean when we talk about emissions? And I think it's interesting to start with this slide. Rudolf Diesel developed the first diesel engine in MAN's workshops in Augsburg in Germany. And you can go to a place in the factory, there's a plaque there where the very first engine was assembled and tested and commissioned. The third engine ever built was in the foyer of MAN's corporate offices there in Augsburg in Germany. And the diesel principle is a combustion cycle that doesn't necessarily limit itself to diesel fuels. It can be a cycle employed in things like natural gas combustion, and it's also being looked at for future fuels like ammonia and hydrogen and the like. So some people are saying that the diesel engine is dead. We may well be seeing diesel fuel as we know it now becoming less prominent, but I think the diesel engine as a technology has some quite significant life left in it, and we'll look a little bit more about that in a second. So when Rudolf Diesel was developing the first diesel engine, I don't think he really had any idea just what, in terms of a pollution or emissions, the diesel engine problems it would develop over the 100 years or so that have elapsed since he first developed the engine late in the 1800s. But the diesel engine, as I said, it does have wide application. It is arguably the most efficient internal combustion engine cycle. It's got very high thermal efficiency. Generally speaking, low unburned hydrocarbons are emitted from a diesel engine. It does lend itself, as I said, to a large range of fuel types. And it's very good in dynamic loading applications in terms of load acceptance and the likes. But the big downside to diesel engines, and this is perhaps something Rudolf Diesel didn't understand himself at the time, but as we strive for more efficient diesel engine cycles, generally we do that by increasing the compression ratio, increasing the combustion temperature, getting more complete combustion. But the downside of that is it can be that it produces more harmful emissions, and we'll delve into that a little bit more in a second. So here we have a typical emissions pie chart, and you can see that very large part of the emissions of a diesel engine are fairly benign substances: nitrogen, oxygen, water vapor. And then you've got emissions that we're more concerned with these days: carbon dioxide and what we call the pollutant emissions, which is a very small portion of the wedge, but they can have quite dramatic health ramifications and ramifications in terms of greenhouse gas emissions. So everyone, I think, knows what greenhouse gases mean, but in terms of emissions from a diesel engine or an engine burning other types of fuels, we're not only concerned with CO2, but we're concerned with things like methane, nitrous oxide, laughing gas, and ozone, and these can have quite detrimental carbon equivalent emissions in terms of the potential greenhouse gas warming effect of those other emissions, and they're essentially unburned fuel and some of the byproducts of the combustion process. And if we drill down into those a little bit more, we've got things like carbon monoxide, nitric oxide, nitrogen dioxide, and this is what we commonly refer to in engine terminology as NOx emissions. And NOx emissions are something that we know has a causal link to respiratory problems and is a major constituent of smog. And NOx emissions in particular can be quite dramatically enhanced by regional factors. For example, we all think of Los Angeles in the 80s and 90s with the huge smog that was evident there, and that's largely because Los Angeles is in a valley, and you get NOx being exacerbated as smog and those pollutant emissions getting trapped in an atmospheric inversion. So if you go around the globe, you see certain parts of the world that, for geographical reasons, are more prone to NOx emissions and smog, or to amplifying the effects of NOx emissions and smog, and Los Angeles is probably the best example of that. Then we get SOx emissions, sulfur oxide. So one of the constituents of diesel fuel is sulfur. Traditionally, the heavy fuels burned in large ocean-going vessels contained quite a large sulfur content, and as we burn fuels with sulfur content, those oxides are emitted and they react with various constituents in the atmosphere, and they can cause sulfuric acid rain and the like. So there's been quite a push to regulate the amount of sulfur in the fuel, and then how we treat those emissions in the exhaust stream. And then you get particulate matter, which is generally speaking unburnt hydrocarbons, ash, condensation, and those things that go into what we would describe as visible smoke. So in terms of global shipping and the picture of shipping and how it sits in terms of greenhouse gas emissions globally, and in terms of the transport sector, shipping, it's not all bad news. Shipping is, it accounts for 94% of all intercontinental transport or trade. It's 71% of all global trade is moved by ship. It's responsible for about 15% of man-made NOx emissions, and it's responsible for somewhere in the range of 2 to 3% of global CO2 emissions. But if you line shipping up against some of the other sort of modes of transport for goods and people, it compares quite well, as this chart demonstrates. You can see shipping there at the top of the bars, and 1.5 grams of fuel is needed to transport 1 tonne of goods 1 kilometre, and that's quite significantly more efficient than trains, trucks, and obviously planes, which have, as you can see, quite a significant issue for moving cargo around. And we're talking in terms of the consumption of fuel in grams is directly correlated to CO2 emissions. So in terms of current and future regulations, this is quite an interesting area at the moment. There's a lot happening. there's been some recent developments in terms of IMO resolutions around how we're going to regulate carbon emissions. This slide here just shows you, it gives you a little bit of an idea of what are the goals or the ambitions in terms of global shipping, and what are the timelines, and what are some of the measures that the industry is looking at implementing to meet those ambitious targets. So you can see that in terms of carbon intensity, there's a goal to achieve a 70% reduction per unit of work by 2050 relative to the 2008 levels. So that's an enormous improvement in the efficiency of the energy efficiency of shipping that we're trying to achieve. If you look at overall reductions, this is obviously taking account for some population growth. We're talking about a 50% reduction in greenhouse gas emissions for the total international maritime fleet by 2050 compared to 2008. So there's a couple of ways of looking at it, but whichever way you come at it, it's quite a dramatic reduction that needs to be achieved. And so if you're talking about regulation and what are some of the measures that have been implemented. So as of, I'm not too sure, I think 2018, they implemented what was called the Energy Efficiency Design Index for any new ship. And this is essentially a formula that the designers or the naval architects looking at a new ship have for the energy efficiency of the ship, and it takes account of the size of the ship and the power required to achieve the design speed, and it looks at a range of factors in determining what the actual requirement is for any particular ship. And so this is something that's already in place for new ships, for anything over 400 gross ton and across a range of different categories of ships. And this is proving quite a challenge even now for some new build ships. And I'm working on a project, a RoRo project at the moment, where the customer has a design speed of 22 knots. And with the currently available technology, it's line ball as to whether they're going to be able to comply with the EEDI requirements, and looking into the future as those requirements are tightened, whether they'll be able to remain compliant. So some of these measures will undoubtedly see existing ships' lives come to an end, some would argue prematurely, and that's going to create quite a bit of work for naval architects, in the sense that that tonnage will have to be replaced with more efficient ships, or ships that are using fuels that don't create the levels of CO2 equivalent emissions. So just working through that list there, you can see the ship energy efficiency management plan. That's an already existing requirement for operating ships, in the sense that they have to have a documented program for improving the efficiency of their ships. There's also regulations around volatile organic compounds. So then if we go to midterm measures, and this is something that's only very recently been ratified by I don't know if it's been ratified by the IMO, but it's been passed by the Marine Environment Protection Committee of the IMO, and this is what you may be hearing a little bit about, and that's the energy efficiency, the Operational Energy Efficiency Index, or the EEXI, and it's very similar to the EEDI, but it's now being applied to existing ships. So if you're the operator of an existing ship in a category, say a bulker, then you have to start complying with ever increasing requirements to improve the efficiency of that ship, or the energy efficiency of that ship in terms of total CO2 emissions. And we're already starting to see customers coming to us asking for ways to comply with these requirements. Probably one of the major things that ship owners can do is limit the speed of their vessel. So we're looking at things like what we call engine power limitations, where we essentially take an engine that, for example, produces 10,000 kilowatts of power and limiting that engine to 8,000 kilowatts, so that the vessel can't travel as fast and it becomes essentially more efficient in the way that it's moving the cargo. The other thing that's recently been endorsed by the IMO, and I think they're still working through the details of just exactly how the formula will apply, is what they call the carbon intensity index. And this is similar to the EEXI, but what it does is create a framework for penalising those existing ships that are not compliant with the EEXI. And there's various ways and means by which they're proposing to do that. But it's something like, you could think of it as something along the lines of an emissions trading scheme, or even perhaps a carbon tax for shipping, for global shipping. I mentioned speed regulation. It's obviously one of the key measures that ship owners have to reduce the energy consumption of their vessels, and that has implications in terms of, if you all of a sudden start operating your vessel at a different speed to the design speed, all sorts of factors come into play, like optimizing propellers, optimizing engines. All these sort of things are looked at and potentially on offer to improve the overall fuel efficiency of the ship. Another area that we'll touch on a little bit later in the presentation, but one area of particular concern is when you're running your ship on natural gas or liquefied natural gas. One of the downsides of burning natural gas as it currently stands in marine engines is that there is some unburnt methane escaping to the atmosphere, and methane is quite a potent greenhouse gas, and this is negating some of the benefits of burning liquefied natural gas in ships. And so there's ways and means that we as engine manufacturers can employ to reduce methane slip or unburnt methane escaping up the exhaust funnel. But they're in their early stages of development, and it's something that, if regulation comes into play, it will drive, obviously faster implementation of some of those measures. And then longer term measures, as you can see from the level of ambition, a few percent here and there in terms of the improvement of the efficiency of a diesel engine is not going to make up for the 70% reductions that are required. So burning low carbon or zero carbon fuels or carbon neutral fuels is very much something that's considered in the medium to long term. This is, I won't go into this chart, but this just shows you the development of regulation around things like greenhouse gas emissions, the Energy Efficiency Design Index, SOx regulations and NOx regulations. And it's sort of a little bit forward looking in that some of the areas that are being talked about for NOx regulation, and it's highlighting some of the the midterm measures in terms of greenhouse gas emissions reduction. So if we talk about NOx emissions, which, as I say, is historically one of the key pollutant emissions of diesel engine combustion, and we're not just talking about diesel fuel, but we're talking about gaseous fuels and other types of fuels. They tend to all produce NOx. When nitrogen is part of the combustion gases, at high temperatures we get nitrogen oxides forming, and as you can see by the chart there, the current areas of NOx or higher levels of NOx regulation compared to the global standard regulations are in Northern Europe and in North America. And if we start to sort of do a little bit of crystal ball gazing, so to speak, we're starting to look at other areas of the world where they've got high population densities, and as I said earlier, geographical conditions lend themselves to the presence of smog and associated pollutant problems, which lead to health issues. China, Japan, they're probably the next areas that will be major targets for NOx emissions. And you can see if those sort of 4 areas implement further NOx emission regulations, that will start to take account of pretty much all global trade in terms of NOx emissions, ships coming and going from various areas around the world. So when we're talking about all these regulations, you know, how do we, I thought it's worthwhile just having a look at, well, how effective is some of the regulations that have been implemented? How effective have those regulations been? And if we're talking about NOx emissions in California, as I mentioned, very stringent requirements. They've had a significant issue with smog. NOx is a very large component of the smog and the pollution issues, the atmospheric pollution issues they've had there. And you can see, looking at this bar chart, that they've been very effective in actually reducing NOx emissions, and that those bar charts there, the large contributor to those reductions is trucking and rail, and where they've got even more stringent requirements than marine. And you can see, as they've implemented those more stringent regulations over the last 20 years, they've had quite a dramatic effect on reducing the overall NOx emissions. And you can see there that shipping sort of remained pretty static over that period. And it's really only now that in North America they're starting to tackle NOx emissions in a significant way. And you can see there that Tier 3 level emissions were introduced in 2016. And it's only now, and probably over the next 5 years or so, that we'll start to see that the benefit of those more stringent requirements flowing through into the trends as far as shipping is concerned. But what this does highlight is these regulations are very effective, and I think it's fair to say that in California there's been quite a dramatic improvement in air quality as a result of some of the systems that we've been employing on internal combustion engines, particularly diesel engines. So one of the things we are able to bring to bear in terms of addressing this issue of both pollutant emissions and greenhouse gas emissions are alternative fuels. And this little chart here just gives you a very good overview of the relative merits of some of the alternative fuels that we're looking at as engine manufacturers. And so you can see there on the top row, you've got HFO, which is the standard marine fuel, something like 200 to 300 million tonnes of HFO consumed in shipping every year. And you can see there that it has a specific energy and energy density, and using it as the standard required tank volume for a given voyage or a given requirement. 1,000 cubic meters compares quite favorably to pretty much all the other fuel alternatives in terms of the tank volume required. The next best being LPG and LPG were pretty close together. These figures don't take account of some of the supporting infrastructure around the tank. So you can imagine that HFO is a fairly simple system in terms of delivering the HFO from the tank to the engine, whereas things like liquefied natural gas require evaporators and vaporizers, I should say, and other quite significant infrastructure just to convert that storage volume into a usable fuel. As you go down the list, you can see methanol there, which is, is in many respects quite a good alternative to HFO in that it's a readily available fuel. It's quite widely traded globally. It burns quite clean if you look at the SOx emissions from it. It's not a huge reduction in terms of CO2, but it has some quite strong benefits in those other areas. And then we start to look at some of the more exotic fuels like ammonia, hydrogen, and then for the sake of comparison, we've added batteries to the chart. And this table doesn't talk too much about the emissions reductions of ammonia and hydrogen in terms of SOx and NOx. But essentially, it's fair to say that we're confident we can have those fuels compliant with the current pollution emission regulations, and then quite obviously burning ammonia or hydrogen, there is no CO2 produced burning those fuels. So they're essentially 100% reduction in CO2 emissions, except for the fact that in the early variants of those engines, we'll almost undoubtedly use a small amount of diesel as a pilot fuel to initiate the combustion process inside those engines. So you can see there, you're getting a bit of an overview of what are some of the relative merits of the different fuels that we're looking at. For example, liquefied natural gas, it's a very readily available commodity. It has enormous benefits in terms of reduction of SOx and NOx. It has a fairly small, it has a reasonable benefit in terms of CO2 reduction, but again, you've got to take account of the fact that there is some unburnt methane escaping, and that has a negative effect on the overall CO2 equivalent or total greenhouse gas emission levels of those fuels. And I'll have a look at that in a little bit further in a second. When you're talking about batteries, and I've been involved in batteries and talking about batteries in the marine environment for ever since I started with MAN, and I think it's fair to say that batteries have a place in the sense that they can be used to optimize the load levels of diesel gensets and engines, but they really don't provide the endurance required for any sort of ocean-going sea trade, and it's not likely in the foreseeable future. So that they have a small role to play in the marine environment in short shuttle runs, for example, passenger ferries moving across rivers and fjords, and maybe even some slightly longer voyages. But it's very hard to see them being involved in intercontinental trade anytime soon. I spoke quite a bit about liquefied natural gas. There's a picture there just giving you a little bit of an idea of the infrastructure. You can see the tank there. It's a vacuum insulated tank. And then you have a confined space at the end of the tank, which is all the gas handling equipment, vaporizers, control valves, monitoring equipment to essentially convert the liquid into a gas. As the previous slide highlighted, there's a 24% reduction in CO2 burning gas. It's a simpler hydrocarbon, and it converts into energy with less CO2 emissions, but that is partially offset by methane slip, which is quite a potent greenhouse gas. So one of the challenges for us as engine makers is to, as I said earlier, reduce the amount of methane that escapes. And there's various ways we can do that. We can scrub it from the emissions, we can recirculate the exhaust, and in doing so recirculate some component of that methane. And they're all very live projects in terms of our development of our technologies. Gas is a very good fuel in terms of particulate matter. It burns quite very cleanly. One of the other benefits of methane is it can be synthesized using without essentially not from a fossil fuel source, so it can be made synthetically. There are variations in the quality of the fuel, and that's reflected in what we call the methane number. Another very interesting area of development is ammonia, and we have set a goal to ship our first ammonia engine and fueled engine in 2024. Basically, when you combust ammonia, there's no carbon in ammonia, so there's no CO2 emissions. There is quite a bit of history with combusting ammonia, although it's not in commercial use at the moment as an engine fuel. We know its combustion properties quite well. It's very similar in terms of the handling and fuel storage to LPG, so it can be stored in essentially a industrial scale barbecue bottle at fairly low pressure, or it can be stored as a liquid at sort of minus 33 degrees C in an insulated containment structure. It's a widely traded commodity. It's a ready fuel source for the existing ammonia carrier fleet. And as I said, we're hoping to ship our first ammonia engines in 2024, and there's quite a bit of interest amongst my customers in Australia, a couple of mining companies in particular, very interested in this technology and very, very much looking to leverage off Australia's potential as a renewable energy powerhouse, in the sense that we can use solar energy to generate ammonia fuel, wind energy as well, and even hydro to supplement those two renewable sources in periods of low wind energy production. So we're working quite closely now with the authorities to develop and have this technology approved. Obviously, one of the concerns, very similar to natural gas, but in some sense even more of a concern, is that ammonia slip is a concern in the sense that any ammonia escaping into the atmosphere is toxic, and we really can't have that happening. So a lot of work going into how we will scrub that ammonia from the exhaust stream. In terms of the fuel source, pretty much all the fuel that is in existence now is produced using fossil fuel energy. So the supply chain for this is a little while off, but certainly we're very, very much committed to developing the technology. And these engines would be installed in ships, sort of 10,000 kilowatts and above. So, 100 metre up to 400 metre bulk ore carriers and container ships. sort of sized vessel. This is just as I touched on earlier, methanol is another potential alternative fuel. Methanol is very similar in handling to automotive petrol. It's got similar toxicity. It's similar in many ways in terms of the safety concerns. So it's a little bit more volatile than diesel, a little bit more of a handful, if you like. But it is the synthesis of methanol is a very well-known industrial process. It's a widely traded commodity. It's a very clean burning fuel. If we can develop a supply chain where methanol is synthesized using renewable energy, it becomes again a very viable fuel for large ocean-going ships. And we have we have a strong association with the methanol production company called Methanex. They've got the world's largest methanol production facility in New Zealand, and other facilities in other parts of the world, and they're using vessels very similar to the one shown there to transport methanol throughout all over the world, throughout the world. So the final section I wanted to present is just what we call power-to-X. And it'll be pretty clear when I show the next slide. So essentially what we're looking to do is pull CO2 out of the atmosphere and using renewable energy and mixing CO2 and hydrogen together to synthesize synthetic fuels, being synthetic methane, synthetic methanol, synthetic diesel, and then pretty much all of the readily available internal combustion engine technologies are able to burn that fuel. So if I'm a ship owner now and I'm wanting to build a ship with currently available technology, I can, for example, put LNG fuel system and LNG engines into my ship, and then as the supply chain for synthetic methane develops, I can run that ship on synthetic methane that's synthesized using renewable energy, and I can essentially run carbon neutral. So it's essentially carbon capture as the drawing shows. And so this is not just an idea. This is now running as part of a pilot program that we're running with a sister company in the VW group, Audi, where we're using renewable energy to synthesize methane using a methanation process and electrolyzers to synthesize the hydrogen. That is then taken from a gaseous state and liquefied, and then that liquefied natural gas is used to power a ship. And we've got a pilot project running in Europe. A German shipping company is running a vessel called the Westermeal, and in 2017 we took what was an existing ship with diesel engines. We converted those engines to dual fuel engines that burn liquefied natural gas and diesel pilot fuel, and now we're blending synthetic natural gas into that the refueling cycle of that vessel. So it's now burning a significant portion, or 20 tons of a 120 ton round trip is consuming synthetic natural gas, and that's reducing the CO2 emissions of that ship by 56 tons per trip. So that's giving you some idea of some of the technologies available, some of the things that we're doing. I'm pretty sure that's my last slide. And as you can see, there's quite a number of range, quite a significant range of technologies available, and there is a significant challenge, and we are working to try and address those challenges, and very much looking to support the naval architecture profession, who'll be at the pointy end of a lot of these challenges in terms of improving the overall efficiency of vessels. So that's it. Thanks very much. And any questions?
So you mentioned about the criteria, but you were talking about a transport work, I think, per unit of transport work. So does that take into consideration the speed of the cargo as well? Because also, of
yes,
course, your carbon emissions are all on the same, or on different speeds, but the transport work, does that actually take into consideration speed of cargo? Because you could potentially, of course, just slow everything down and do it lots and lots of times.
Yeah, I mean, it doesn't, it looks at the power required. It's quite a complex formula. I don't fully understand it, but it looks at the power required to achieve the capacity, the size of the ship. So if you, as you know, as you go up in terms of speed, the power requirements can become quite dramatically more. So essentially, if you're burning more fuel or requiring more energy to travel at a higher speed, then you can become non-compliant in terms of the design. And one of the ways to become compliant is obviously to reduce the speed of the vessel, the design speed of the vessel. I hope that makes sense. I'm not sure.
Yeah, I think what you're saying is the speed is not necessarily in there. So you could actually simply slow things down and become compliant. And then
that's right, exactly. Yeah. And that's one of the major factors that I'm sure the authorities envisage.
Yeah. There's a bit of a problem in that you could just become compliant by having lots and lots of small boats going very, very slowly. But you probably don't actually reduce the overall effect on the planet. But that would be quite difficult economically, though. I suppose that's what they're relying on.
Yeah, look, I think there's a hell of a lot of debate about the EEDI and the EEXI and just whether it is an accurate representation. I think everyone acknowledges it's got a lot of shortcomings in terms of some of the anomalies that it produces from one class of vessel to the other. But I think they've just taken a pragmatic view that, you know, there's going to be exceptions to the rule, but well, there won't be exceptions to the rule, but there's going to be anomalies, and they're just accepting those.
So I think there's a couple of questions online. We don't have too many people online. So
sure.
John Fan, did you want to ask a question, or can I just read it out? Maybe I'll read it out. So John asked, may I ask, how will you deal with the after gas emissions for ammonia fueled engine? We use an after treatment to remove some of that.
Yes. So they're looking at there's a couple of, well, firstly, if you go back to the combustion process with ammonia, we can burn ammonia in a diesel cycle, where we inject the fuel essentially at top dead center, and or we can run the engine on what's called the Otto cycle, where it's an air fuel mixture inducted into the combustion chamber and compressed as an air fuel mixture. So those two processes have various pros and cons in terms of the production of NOx and laughing gas and the likes. And so if we go for the Otto cycle, we get much lower production of those elements, and then we install an after treatment system, a knockout pot or an oxy catalyst to scrub those emissions. So there's quite a bit of ongoing research into exactly how we'll do that, but I think the overall view is that we're quite confident that can be achieved without too many issues. And what it may mean is that the engine, for example, starts on a full diesel cycle, running fully diesel fuel. It comes up to operating temperature, and at operating temperature, things like catalysts and all of those things become quite effective in removing some of those pollutant emissions from ammonia. And you know, there may be some additional complexities in terms of managing engine temperature in an ammonia engine as compared to a diesel engine, where we can allow it to fluctuate, you know, quite significantly at low load compared to high load and things like that.
Thanks, Robert. Ahmed had a question out there. Ahmed, did you want to ask that question yourself? It's a very controversial sort of question.
Hi, John. How are you? And hi, Lachlan. Thank you so much for the interesting presentation, Lachlan. So this is Ahmed Swedan from UNSW, Canberra. I'm just wondering, yeah, hi, Lachlan. How are you? I'm just wondering, yeah, about the nuclear power as an alternative source of fueling for the grey vessels mainly. I know that it might be out of your area of scope, but for sure that's like a competition market. So
yeah,
what do you think about nuclear power?
I believe it's something that's being talked about. Certainly, there's discussion about micro reactors and the likes. And I understand that even many years ago, there was a small fleet of nuclear powered commercial vessels. I don't know where I read that, but so it's not unprecedented, and it's certainly not something that's been totally ruled out. I think, and I'm not speaking on behalf of the company, but I think there's always the concern about the level of competence and expertise required to operate and maintain something like that. And obviously there's always concern too about the risks in the situation where it's not correctly operated. So I think it's definitely something that's a viable technology. Whether it's proves to be economically viable remains to be seen. But I do know there is discussion about it, and I have heard it in some of the forums that I get engaged in.
Thank you so much, Lachlan, and thanks, John, for the time, and good to see you, man.
Good to see you too, Ahmed. So are there any other questions around? I might just, Lachlan, whilst I've got you, just one last little issue, I suppose, just the carbon capture. So that seems quite fascinating. So that was fully retrofitted to that vessel and has been operating successfully, and basically kind of, I suppose, recycles the carbon. Is that one way of the GHG emissions? Or
yeah, so the image is a little bit misleading in the sense that the carbon capture is not actually taking place on board the ship. The carbon capture is taking place during the synthesis of the fuel on shore in this pilot facility. So they're basically taking water and electrolyzing the water into hydrogen. They're capturing the CO2, and through the methanation process, synthesizing the CO2 and the hydrogen into methane. And then that methane is liquefied, and then that is stored and transported to the ship, where it's bunkered into the LNG fuel system on the ship, like traditional fossil fuel LNG. So it's not actually taking place on board the vessel. It's synthesis, and this is something. For example, you might be aware that Spirit of Tasmania are looking, or they've placed a contract for 2 new vessels. With some of the discussion around electrolyzing hydrogen in the Bell Bay area, it's quite possible that this could be a potential fuel source for those ships.
So it's really in the refining process.
That's right.
So
methanation is a well-known process, a reactor, where you can synthesize them.
So as long as the vessels can take LNG, that's all fine. Is that right?
That's right. So there's absolutely no impediment to existing dual fuel or LNG engines running a synthetic fuel as opposed to a fossil fuel. And the same can be said for synthetic diesel, synthetic methanol. It's just a slightly different chemical process.
Any questions here? Oh, yeah, sorry, Luke. Yep.
Lachlan, is this mostly aimed at two-stroke applications, or is it also a sort of high-speed four-stroke as well?
Sorry, Jonathan, could you just repeat that? I was struggling to hear that.
Yeah, is it sort of, are we aiming only at the two-stroke, this sort of technology, or is it also something on the high-speed four-stroke as well?
So these technologies, if I understood the question correctly, you're asking, does it apply to two-stroke and four-stroke engines?
Yeah, that's it.
Yeah. So, for example, ammonia, we are very much well into developing an engine that will combust, a two-stroke engine that will combust ammonia. And as I said earlier, we're going to targeting first deliveries of that engine in 2024. We're also developing ammonia combustion for a four-stroke. One of the issues with things like methanol and ammonia is that, as you saw earlier, the energy density of the fuel is a lot less. So we need 4 times the volume of ammonia to get the same bang. And so the injection equipment on the engine, the volume of the fuel that the injection equipment needs to inject at each combustion cycle is quite a lot larger. So if we're talking about a large two-stroke engine on a big ocean-going vessel, we've got plenty of space for all of that type of equipment. If we're starting to talk about smaller four-stroke engines, we're really starting to talk about redesigning a lot of the cylinder head, and extra space is required. There's quite a lot of extra considerations. So the development of a four-stroke engine to combust things like ammonia and methanol is a little bit way behind where we're at with the two-stroke process. But definitely there's development going on in both areas. And it'll, look, from a practical point of view, it'll be the larger powered engines that get the development effort, because that's where most of the requirement is in terms of the IMO. And obviously the larger ships are responsible for the much higher proportion of the global emissions. So it's fair to say that whether it's two-stroke or four-stroke, our focus is on larger engines in terms of developing the technology.